Hey everyone. So today I wanted to talk to you about the Bohr model and why Niels Bohr thought that this model was the correct model of the atom. I want to look at why this model was so popular and why it affected us even today. Okay, so let me give you a little bit of backstory. So in the early 1900s, talking like 1905 or so, at this point in time, the nuclear model is the widely accepted model of the atom. That's the one with the nucleus where the electrons are all orbiting it, but all the electrons are roughly the same distance from the nucleus. Okay. Now, while this is going on, another scientist named Max Planck is doing research on heated materials. And what Max Planck was interested in was when you heat up materials like iron, okay, like you can see in this picture, it'll begin to glow. But if light is a wave, when these materials heat up, they should glow every color in the visible spectrum. You should see all the colors of the rainbow. But that's not what we see. If you look in this picture right here, you can see that this iron bar, when it's heated up, it definitely has a bunch of different colors, and that's largely dependent on how hot the metal is at that given spot. But it's not all the colors of the rainbow. There's no blues, there's no purples, there's no greens, none of that, okay? There's white, yellow, red, orange, kind of a dull red as it cools down, and then black. And Planck could not really explain this other than to say that it's possible that when energy is released, it's released in very small chunks. Okay. And at a certain point, there's a minimum amount that can be released. You can't release less than that. So if I were to explain that, right? Let's say that I wanted to give somebody, let's say that I was building a house out of Legos, okay? Now I'm going to use like larger Legos to kind of illustrate this, okay? For the sake of, argument's sake, let's say that all the Legos are kind of stacked up on top of each other, okay? Now, I can make that house or that building or whatever it is. I'm not the best artist. I can make this basically as tall as I want. Okay, I just keep adding more and more Legos, right? But if I wanted to make this as small as possible, right? So like let's say I started, getting rid of Legos, okay? At a certain point, I'm going to get all the way down to the point where there's only one Lego left. Okay? And no matter what I do, I can't have smaller than one Lego. I can't lose half of a Lego. Okay? So basically, at that point, if I want to lose more, I have to lose this entire Lego. Okay? So basically, what Max Planck was saying was if you had like some amount of energy, right? At a certain point, that total amount of energy is broken into really, 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 really small pieces. But each of those pieces has a specific value. And so because of that, he believed that this minimum amount of energy was directly causing what he was observing. Okay? He proposes what's called quantized energy. Now, you've probably heard of this term before, or at least heard something similar to it, because this experiment is the foundation of what's called quantum physics or quantum mechanics. Okay, this quantized energy ends up revolutionizing the world. Okay, so fast forward a little bit. Okay, a scientist named Niels Bohr is working in England, and he sees Max Planck's work, and he sees what Max Planck is dealing with. And Bohr says, I can explain that. Okay. And what he does is he proposes a brand new model of the atom, which becomes known as the Bohr model. Okay. He changes up the model. Instead of having all the electrons orbiting at the same distance away from the nucleus, he has them on different rings that are working their way out from the nucleus. And he calls these rings energy levels. Okay. Now he also sometimes calls these shells, but they're kind of the same deal. Okay. Now each shell is a different distance away from the nucleus. So like this is shell 1, this is shell 2, and this is shell 3. Okay. Now Bohr does a lot of work with hydrogen. Okay. So hydrogen has 1 electron. Now what Bohr says is that electron is going to exist in the lowest energy level possible because that's where it's most stable. And the lowest energy level is the one that's closest to the nucleus. So I'm going to draw my Bohr model for hydrogen. I'm just going to put my 1 electron on here. Okay. Make it nice and big so you guys can see it. Okay. So there's my electron. Okay, it's right here. Now, Bohr says that the electrons can only exist on these rings in these energy levels. And he says that these electrons can never exist anywhere but these energy levels. Okay? And Bohr points to the experiment done by Max Planck as evidence of this. Now he's able to replicate this in his lab, and he gets some really, really interesting data. What he realizes is that when an atom is in its normal state, okay, he calls this its ground state. And the ground state is just the atom's most stable state. Okay. But he says atoms don't have to stay like this. Okay. In fact, atoms can absorb energy. And he points to Planck's work. Okay. He says when an atom absorbs energy, whether that's through heating or electricity or whatever, the electrons in these rings can actually jump to higher rings. Okay. So this electron right here can actually make a jump to the next ring up. Now, when this atom or when this electron jumps up to the next ring, Bohr calls this an excited state. And that's where electrons move to higher energy levels. Okay, but Bohr says they can't stay this way. They don't want to stay this way. The energy that they're absorbing is basically forcing them to be this way. So what Bohr says is, inevitably, that electron that has jumped to a higher state is going to eventually fall back down to its ground state. Okay? Now, when that electron absorbed energy, okay, this first arrow right here, the one in the red, this is energy going in. Okay? But this blue arrow right here, when that electron falls back down to its ground state, that is energy going out. And that energy going out is released as light. Okay? So, basically, according to Bohr, atoms, when they absorb energy, their electrons move up, but they can't stay that way. So, when they release energy, that energy is released as light. Okay? And Bohr states that because these rings are specific distances apart from each other, it takes a specific amount of energy, an exact measurable amount of energy for an electron to jump from ring 1 to ring 2, for instance. And so, when that energy is released, it releases again that specific amount of energy. Now, there's a math equation behind this, but when you mix it with Planck's work, what that means is that specific amount of energy that's released is released as a specific color of light, one color. Because a specific amount of energy is coming in and a specific amount of energy is going out, that amount of energy corresponds to one color only. Now, why is it that these items can glow multiple colors? Bohr says that's simple. Because there's actually more than one possible jump. Okay? For instance, this electron, let me clean up my picture a little bit. So before, I had this electron going up to energy 2, or to energy level 2, and then back down to 1, right? And that would be a specific color, right? So let's just pick a color, right? Let's just say that that is red. Okay? That electron could also jump up to energy level 3. It could go from 1 to 3. And then that same electron could fall back down from 3 to 1. Okay? Now that's a bigger jump, so it's going to take more energy. So let's say that this is blue. Okay? We're just making up colors right now. Okay? But it could also jump up to level 3, and then it's going to fall back down, but instead of falling straight back down to 1, it falls down to 2, and then it falls back down to 1. Okay. Now we've already established that going from 2 to 1 is red. Okay. So the red might be brighter, for instance. It might be more intense. And the fall from 3 to 2, that could be, I don't know, yellow. Okay. Now remember, there's more than 3 energy levels. There's basically infinitely many, but we really only go up to 7 on the modern periodic table. So what this means is there's all kinds of different combinations that an individual atom can do, depending on how much energy is absorbed, how much energy is released, and how that energy is released specifically, whether it's like stepwise or all at once. There are many different ways that this can happen. Okay, so as a result of this, okay, just heating up this one type of material, you're going to end up with red light, yellow light, and blue light. But you would not see green and orange and violet and things like that. Okay, it's specific colors because specific jumps are being made. Okay, and this was the experimental data that Bohr was seeing that caused him to develop the model that he did. Okay, that is why Bohr said that the electrons can never exist in between, because if they did, then that energy would be affected by other things. Okay, it wouldn't be as consistent. Okay, so hopefully this gave you a better understanding of what are called ground and excited states. If you have any questions, come see me anytime. Until next time.